Okay, this video is about how to modify a mini split to be a geothermal ductless mini split. First, we're going to start with a video of the final product, and then we'll get into all the hows and whys. Here's what's left of the outdoor unit to the mini split. And down here is the motor that usually is connected to a fan in the mini split, but now it's connected to a pump, and that pump is flowing water outside through the loops, ground loops. Then over here there's a circulating pump that's coming off the side of the tank here, and then that's just flowing into that pump and then back into that tank just for extra circulation when it's needed, which is infrequent. Now we'll look at inside the tank. So looking down in here, we can see the evaporator. We can see two temperature probes. So one is coming off from the mini split. The other one is controlling that circulating pump. So below a certain temperature, it'll kick on. On the left, there is a return line. That's a circulating return. On the right, that's the circulating return from the ground loops. Over here we have, this is coming from that pump right there. So we're measuring temperature and pressure, and then it's running out to the field. Then just below that we have the circulating pump here, and then that is measuring pressure again, and then that's just going right back into the tank. That can also go out to the field, but right now it's not doing so. Then up here we have, this is the return line from the field. We're measuring temperature, and then we're measuring flow right here. Now this pressure flow sensor has a large pressure drop across it, so I actually have a bypass valve, and that just allows the flow to avoid that flow sensor. Okay, so now the rest of this video is going to talk about, so why would you do this, the system, how I size this system. We'll get into a system schematic, the trenches, modifications that you have to do to the air source heat pump to make this work, the operation of the system since then, how it's been performing, and the system costs. So first of all, let's talk about why a ground source heat pump. So right now I heat with wood exclusively. The cats really like it, but they don't really have to light the fire at all, and they don't have to do any of the work. So the other problem with a wood stove is you wake up in the morning, you light a wood stove, and then by the time you leave, it's just starting to get warm. So I'd like to be able to just flip a switch and not have to worry about it. So the other problem with modifying our heat source or getting a new heat source is that we have no ductwork or baseboard heaters, so that would have to be installed, which is a major expense. I'd rather not use fossil fuels, and I'd rather just install solar, which I plan to do in the next couple of years, and hopefully run the whole thing, the whole house, and all this geothermal on solar. So an option is just to use air source heat pumps. So the pros for those are they are cheap. 2,000 to 3,000 for an 18 to 24,000 BTU per hour system, which is what I installed. They are DIY. You can install them in a weekend, no big deal. The cons are that they have low heat output when it is coldest outside, so you need to oversize the system. So if I need a 24,000 BTU system, I actually need to buy a much larger system. And let's get into a little bit of that. So so here is a chart of temperature, outside air temperature, versus the output of that system. And this is for a set temperature inside of 70 degrees Fahrenheit. So if the outside air temperature is 38 degrees, this unit will output 18,000 BTUs. It's an 18,000 BTU system, so it actually puts out that right at 38 degrees. Now, as the temperature outside decreases, the amount of heat it can output decreases. So now if you go down to 10 degrees Fahrenheit, now you're at like 13,000 BTUs, so like a 30-something% drop. You go down to 0 degrees, now it's only putting out about 10,000 BTUs, almost half, almost cut in half what the output of that system is. So that's a drawback. Now also, not only does it put out less heat, but it's less efficient, which isn't surprising. So the coefficient of performance, That is a measure of how efficient the system is running, and we'll get into the calculation for that. But for this system, the COP, so higher number is better. So at 38 degrees, it's right about 3.0 is the COP. And then if you drop to say 10 degrees, now it's like 2.3. And if you keep dropping the temperature to like 0 degrees Fahrenheit, now it's the COP is 2, which means half the heat energy is coming from electric and half is coming from the ground, where at 3 it's 1/3 of the energy is coming from electricity and 2/3 would be coming from the ground. So it's a major hit. So other options are to just use the ground source heat pump. So the pros are they're very efficient. So it's the efficiency is based on the temperature of the ground, and the ground temperature is quite constant. So another benefit of these systems is the heat output is not impacted by outside temperature. So like we saw that penalty for lower outside air temperatures, that's not a problem for a geothermal system. So, but the cons are, the obvious con is the expense. So these are much more expensive systems. I had quotes in the $50,000 to $90,000 range for my 2,000 square foot house, and I really only use about 1,000 square feet of it when my children aren't home. So the major half the cost of that, or a little less than half the cost of that, is ductwork. They wanted to install ductwork all over the house, so that would be a major expense. The other problem with the ground source heat pumps is that they do not come in sizes that would really fit my house. So I really only need something in the 18 to 24,000 BTU per hour, and the smallest systems they make are on the order of at least 3 ton. So not a real good fit. So how did I size the system? So I currently heat with wood. So the max amount of wood I've ever burned in a winter is probably 3 cords, maybe less. And that was when we were, I think, heating the whole house. So I think I actually burned much less than this. So 3 cords. 3 cords is about what I burned, so that's 54 million BTUs per hour per year. So then looking at the month of January. January is my coldest month, the greatest number of what they call heating days. So for my location, 19% of my heating is done in January. And then so I just wanted to look at see how big of a system I would need to heat in the month of January. So according to these calculations, I need 14,000 BTUs per hour, and that would be continuous, but 14,000 BTUs per hour for on average in January. Now, my worst case day is quite a bit more. So assuming a 0 degree Fahrenheit day, which the heating average temperature for January in my location is 25 degrees Fahrenheit. So worst case day is 0 degrees Fahrenheit. So now we're talking 23,000 BTUs per hour, 22,000 BTUs per hour. So, but realistically, I do not need to burn 3 cords of wood. My house was 75 plus degrees when I'm burning wood, and I was heating the entire house. So I'm using less. And then the other thing is, if I have really cold days, I don't mind lighting a fire here and there. So I actually decided to go with a 18,000 BTU per hour system, and I also didn't want to spend a ton of money because I didn't know how this was going to work out. Okay, so let's talk about sizing the trenches. So in general rule of thumb is you need 600 feet of buried pipe per 12,000 BTU system. So I have an 18,000 BTU system, so I need 900 feet of piping, and I oversized. I really did more. I was targeting like an 1,800 feet of piping. It's probably more in the 16 to 1,700 foot range. I didn't quite make my trenches quite long enough, but I have 300 foot trenches roughly, and this is the layout. So this is my septic system, and here's my drilled well over here. And so these are the plans that I gave to the town to do this project. Okay, so let's go over a system schematic. So this is a layout of a general mini split, roughly. So you have, there we go. Okay, so you have vapor that enters a compressor, and this is for a mini split in heat mode. So you have a vapor that enters a compressor that's at low pressure, and it goes through the compressor, comes out at high pressure, high temperature. It goes to the air handler in your house, and you blow air across that. That air will be, say, cool coming into it, and then it will be warmer coming out. At the same time, in the opposite direction, your vapor in your refrigerant is at high pressure, we talked about, and then it comes out. This is a condenser, so it actually changes from a vapor to a liquid, and it's still at high pressure and probably fairly high temperature, but then it goes to an expansion valve that reduces the pressure and the temperature very low, and then it gets to your evaporator. So now you're blowing cold air. This is outside usually. In general, this is outside, so you're blowing that air across the evaporator, but so it blows that air across, which is cold, but then it's really cold when it comes out because it's just helped to evaporate, going from a liquid to a vapor, and that's your heat pump cycle there. So what I did was I modified this, and so I installed a tank. So here's the tank here. So I put that evaporator or heat exchanger into a tank, and so then that liquid comes out of the tank, is pumped into the ground loops, and we'll get into this. I guess we'll hit this right now. Here we got a temperature measurement. Here we got a pressure measurement. Goes through this, and then comes back. Then we have a temperature measurement, and then we have a flow measurement, and then it goes back into the tank. So this is how this operates. This pump here is flowing at about 5 gallons per minute, and then to make sure that this coil here this heat exchanger doesn't freeze, which if you put the heat pump in turbo mode, sometimes you get ice on the surface. So I installed a circulating pump to pump water just around this so that it's not getting real cold right on the surface of the heat exchanger. So this is flowing at like 20 gallons per minute. So this is a Taco 0014 circulating pump that kicks on based on a temperature inside the tank, right on the heat exchanger surface. Okay, let's talk trenches. So we need to talk about the depth of the trenches. So this is a chart of the ground temperature at different depths throughout the year. So this is January, February, March through December, and this is for a warmer climate, but I think it's representative of what happens anywhere in the world. So here is January, and here is the ground surface. So the ground surface is at its coldest in this location on February 4th, which is probably pretty normal for any location. Is somewhere in January, February is your coldest temperature, and then it's peaking somewhere in August, and then it's dropping back down. So that's your surface temperature. Now, if you go down 2 feet, the variation is slightly less. So now you don't get quite as cold, and it also shifts a little bit later in the season. Now, when you go to 5 feet, so we're going to say 62 is the average, and so it goes down to, like it's about 50 maybe there's actually like a 12-degree difference from the average, and it's also shifted further later in the season. Now, if you go all the way down to 12 feet, now you see that this curve is really flattening out. And what's really important also is not only are your ground temperatures warmer when it's critical, December, January, February, but it's also shifting this temperature to the right. So if we look here, we're getting our min temperature way out in April when we're not really doing much heating. So the critical months are quite a bit warmer. So the take-home message here is go deep. And then I would be remiss if I didn't mention that you really need to check out Garrett Glaser's videos. You should see the link in the description. He explains this very well, and he has a great deal of information about installing ground source heat pumps. Not mini splits, but ground source heat pumps in general. Okay, so trenches. Let's talk trenches. So you need to avoid, when you're wet. So for my location, my ground is fairly wet throughout most of the year. So I needed to really plan this well, and I had to actually not do this the year I wanted to because it was just too wet. It rained in August. September is usually dry, and it was very wet. So you want to try to avoid rain as much as possible because you don't want to be digging these trenches and have it start raining. So first I started with a neighbor's tractor. This was definitely a mistake. Needed tune-up, needed hydraulic lines were blowing, leaks were all over the place, and it's just not really a big enough machine. So I ended up paying somebody to come in. Again, not really a big enough machine, but it was a friend of a friend, and it the price was good. So, but I mean, it was such a small machine. He actually dug dug a trench first, a wide trench that he could fit his machine in, and then dug down to try to get to the, I was aiming for 9 to 11 feet, and for the most part we got there, but I would have liked to even been 12. So I would recommend a much bigger machine than this. This was a total pain, and you want to be 3 feet wide, and ideally you want to be 3 feet wide, and you want to be 12 feet down. Okay. So other things, so my trenches were filling with water, which was a total pain. This is only, it was only the first foot or something that I was getting water in, and I could pump it out. But definitely a pain, but it's also a good thing because that means I'm at the driest time of the year now. Now I'm in February, and there's guaranteed that my pipes are sitting in some moist soil, so it's going to be good for heat transfer. Okay, so I put sand above and below the coils so that they don't get damaged when you're backfilling. I had planned to use HDP SDR11, which is the standard pipe for ground source heat pumps, but there's no suppliers near me, and the shipping costs basically doubled the cost of the pipe. So PEX A is also an option, and that's available from Ace Hardware and Home Depot. So I use that. The thermal conductivity of PEX A is slightly poorer than HDPE, but it's just a few percent, so I went with it. I installed, again, these are slinky loops, and I would again advise checking out Garrett videos. He goes into detail on how to make the slinky loops, and that's what I followed. Okay, so what fluid? So typically you use a propylene glycol, and you add about 20%, typically in my location, to avoid freezing. But it's not cheap. It's $200 for a 5-gallon bucket, and I probably need a minimum of 3, maybe 4 buckets of it, plus shipping. Probably would have been at $1,000 in this propylene glycol. So, but I really wanted to avoid it for the following reasons. So one, it increases the viscosity relative to water. So I'm definitely pushing my circulating pump, my ground source circulating pump, as to its extreme. So working it any harder would not be a good idea with more viscous fluid. The other thing is it reduces the Reynolds number. That's a measure of the turbulence of the flow, and that's the whole point of this, is to have turbulence so that you have good heat transfer in your pipes. Again, it lowers thermal conductivity. It has a lower thermal conductivity than water, which is also going to hinder some of the heat transfer. And it also has lower specific heat, so it can't transfer as much heat for the same flow rate. So I decided to go with pure water. I've also put a growth inhibitor in there, so there's not a bunch of fungi growth or whatever else growing in there. I used a cheap RO filter to pre-filter, so it's pretty much pure water. Okay, so let's get into the modifications of the system, so of the heat pump. So the evaporator. So I did not mess with the refrigerant. So I did not cut any refrigerant lines. It comes pre-charged, and I did not want to have to do anything with that. Obviously, I'm not qualified. I'm not an HVAC person. So so the first thing is to just start tearing the system apart. So I just remove the covers here. Next thing is take off the fan, take the motor off, take the brackets off, take anything off that's holding down the evaporator coil. So this is the evaporator or heat exchanger unit. They call it an evaporator, but it's a condenser if you operate unit for cooling. Okay, so then the other major things are right here. So this whole coil is going to be turned 90 degrees down so I can put it in a tank. So these pipes will be bent. These bend very easy, but up here, this does not bend easy. I tried putting pipe benders on there, and I have some experience with that, and these guys did not want to bend well. They wanted to kink. So this was the major challenge, which I'm not real happy with the results. To do it over again, I might do something differently, which I would talk about in a minute. The other thing is, so here I am. I'm starting to bend this now. It's bent down at maybe a 45-degree angle. At the same time, I'm bending these guys because this is how they come. Like they got a 90 bend on it. So I started bending this straight, and then eventually I got those pretty straight, so I can put them right straight into the tank. So the recommendation here is that I would try to find an HVAC person that's willing to remove the refrigerant for you, put some new lines, braze some new lines in for you. Or maybe you can do it yourself, but you need an HVAC person to take the refrigerant out and then recharge the unit for you after it's pressure tested and vacuumed down and all that. Okay, so then the tank. This is the 55-gallon tank that I bought. So turn it on its side and cut a big hole in there so I can drop the evaporator in. And then there's a lid on the side. Now on the side of the tank, you need some special epoxy to try to get that thing to seal. I made a nice window so I can look inside, just for the heck of it. And then there's bulkhead fittings that I installed on various sides of this thing as well. Really important, so there's a heater coil on the base of the unit. This is so if there's ice starts forming on an outdoor unit, it wants to melt that ice. It's got some temperature sensors that are actually on the front of the evaporator, and at certain times it's going to turn on this heater. That's a big problem, depending on where that heater is, if that turns on. So it's best thing to do, and absolute, I would say, necessity is just unplug it. So you have to disconnect these wires right here and just remove the whole thing and get rid of it, so you don't have to worry about that thing is ever going to kick on and start a fire. Okay, so let's talk about the fan motor and then connecting that to a pump. The motor is quite odd. It is a 900 RPM three-phase DC motor. So anything that you're trying to spec out for this, you need to consider that 900 RPM number. So the other thing is I need the reverse direction of the motor, so that's pretty easy. It's a three-phase, three-wire motor, so you just switch two wires and it'll reverse the direction. Okay, so here's the original fan motor, and then so I just made wooden brackets to mount it together. You need a coupling to go from one shaft to another. This is 3D printed. I had one of these 3D printed and it failed, and that was just interim anyway. So I ordered aluminum. I have the aluminum. I haven't installed it. This one hasn't failed yet, but when it does, I'll replace it with the aluminum coupling. And then here's the the pump head that I'm using. This is a Procon rotary vane pump, and there's the part number for that. So the one issue with this that remains is that the heat pump occasionally reverses direction. So this is to like blow out leaves or something that's accumulating onto the outdoor unit, assuming it were outdoor. The problem is that when that reverses, this pump, I think it's cavitating. It's trying to suck water back through all the lines that are outside, and that it doesn't want to do that. So I haven't actually resolved this issue yet. I have some ideas, but if you have any ideas on how to get around this, that would be great. Greatly appreciate it. Okay, so the circulator pump. So again, this is looking down. Okay, so you can see it's actually ice buildup on both sides. This has been shut down for about a half hour. It's a whole layer of ice on that. Okay, so this is the evaporator, so there's ice on this. This was actually really early on when I first installed the system. This was running with a, let me get my pointer. Okay, so this was running with a 2.5 gallon per minute pump. Now I'm running a 5 gallon per 5 gallon per minute pump. So that took care of most of this icing issue, but not all of it. So then I decided to install a circulator pump, and so now that circulator pump is triggered on by a thermocouple that's right on the surface of the heat exchanger. So when it gets below, actually it's 36, so there's hysteresis from 36 to 37. So it turns on at 36 and it turns off at 37. So so here's the circulator. So there's the bulkhead fitting where that's pulling off, and then here's the circulator pump. The Taco 0014 is the model I'm using, and then here's the thermocouple that's controlling that, and there's the circulator return. So that's where that water's coming back in from the Taco pump. And then I'm using this Inkbird temperature controller. You can use, this is a dual temperature controller. You only need a single. Okay, so all right, let's get into operation and a little bit of the details of how this has been going. So I've been running this about 2 months, and let's just for reference, here are my temperatures. So here's the year, and here's the temperature in degrees Fahrenheit, and this is all temperatures at a local weather station from 2000 to 2022. The blue solid line is the average mins, and then the orange one's the average highs. And so so averages in January, February is in the around 20, around 35 for highs. So but we're all over. So yeah, so that's what I'm looking at for heating requirements for our location. And now let's get into what we're doing for measurements and calculations. So for the ground loop, we're measuring the supply temperature, the return temperature, and the flow rate. And let's take a look at where those are. So again, here's the temperature measurement. So we're measuring that temperature there. We're measuring the temperature here. And we're measuring that flow. And then we're measuring the electrical power for the heat pump. And then we're also measuring the current for the circulating pump. Okay, so what do we do with that information? So for the ground loop, knowing these parameters, the temperature and the flow, we can calculate how much heat is being extracted from the ground, and then knowing the heat capacity of the water, we can do that calculation. So then for the electrical power, knowing the amps, we know the voltage, and then we can calculate the electrical power that's consumed by the heat pump. And then we use that information to calculate the coefficient of performance. So this heat pump, this energy that's being extracted from the ground, we add that to the electrical power that's added to the system, and then we divide that by the electrical power, and that gives us our COP, or coefficient of performance. Okay, so actually let's get into some data here. So here's February 20th, 2025. At the bottom here, this is just one day, so it's from midnight to midnight. And first, what we're going to do is look at the temperature. So over here is the temperature for that day. So what we're looking at here is about at midnight is about 15 degrees, dropped down to about 8 to 10 degrees just before daybreak, and then it starts to rise up to like 31 or something, and then it starts dropping again. So that's the outside temperature, and keep in mind this is the temperature that the mini split would see if it were just operating as a normal mini split. Okay, and so now here's the temperature that the heat exchanger was in my tank. So I have a thermocouple that's right next to the heat exchanger, and so this is the temperature we're seeing. So it's from about 35 to 38, 39 degrees Fahrenheit. And there's a bunch of wiggles in this, and we'll talk about why that is. So up here, I'm showing what the temperature was that I had set the system to. So this is rough. So from here to here, it was set to 62. Then at 4:30 in the morning, I get up and I set it to 72. Then at 7 something, I turned it off, and so then the water's just sitting there. Then in the afternoon, we set it to 62 again. This time comes on automatically. Then somebody actually comes home, turns it up to 72, and then it does some wiggles here, and then eventually we set it back to 62 for overnight, and there it is. So you see that there's this drop in the temperature in the system when it's at 72 degrees, which is not surprising. It's pulling a lot more energy out of the system. Okay, so then overlaid with this as well is COP. So this is our coefficient of performance. Remember that higher is better. So at night when we're only operating at 62 degrees, it's pretty stable at like 4.8. Then it must have been getting a little bit colder. As you can see here, it's colder. And so it needs to draw a little bit more energy. Now the COP is between 4.2 and 4.8, bouncing around. Then when you set it to 72, it really drops. So COP is less than 3, around 3, bouncing around. And then the afternoon, it shoots up, and it's in the 3 to 4 range for a lot of the afternoon. House is probably pretty cold after sitting all day, and then it's oscillating, and then at night it goes back up to like 4.4 when we have it set to 62 again. So I would say that's good. So I think one of the main things to take away from this is like, so here's the heat exchanger temperature, and here's your outside air temperature. This is how this system would be running based on this temperature here instead of this red line. So we're doing, from an efficiency perspective, that has a major impact. And the COP, I would say the COP is decent for this day. It's a fairly, it was putting out quite a bit of energy for the day, and it was, I think the average was like 3.5 for that day. One item of note here. So we looked at this chart previously. It was a little bit simpler, but now I've added some lines here. So again, this is outside air temperature, and this is your COP of this system. So but I've added lines here. So this is the set temperature in your house. So as you increase the set temperature in your house, the COP, or the efficiency of the system, decreases. So at 40 degrees Fahrenheit, it drops, say, from a COP of 3.5 to like 2.9 when you go from 60 degrees set point to 75 degrees set point. So that's what we were seeing on that chart. So the higher temperature, when we were setting it to 72, we saw significant decreases in COP, and that made sense. But thankfully, we weren't, say, when it was 10 degrees out, if I did that, our COP would have been down here at 2.1 instead of 2.9. Okay, so another chart here. So this is same COP, same data, same date. So exact same data, slightly different scale. So here's that same COP data. Now I've added on here the power output. So this is the powers over here. The units on that are over here. So at midnight and throughout the night, it looks like it's putting out between 7,500, 8,000, maybe a little more BTUs per hour. Then when we set it to 72 degrees in the morning, you can see it shoots up to almost 18,000 to the rated power, and then it comes down because the house is warming up, so it doesn't need to put out as much. It's getting close to its set temperature, 72. Then we turn it off for the day, and then it kicks on at 62, but the house is cold, so it shoots up, then it comes back down. Then I set it to 72, it shoots back up, and then it modulates, and then we get back to our 62 at night, setting overnight. So now it dropped to like 7,000 or something, because I think the house is warm, so it doesn't need as much energy, and I think it was a little bit warmer at night anyway. So that's showing how that system behaves throughout the day. The other thing is our circulator pump. So this was a fairly cold day, and the system was running pretty strong during these events. So the circulator pump did kick on, not at night at all. So this is the amps. So this is 0 amps, and this is 1.3 amps. So this circulator pump kicked on and ran for those hours. Then it's off during the day. And again, it was on the entire time we were at 72 degrees, and then it kicked off again. Okay, so last thing we're going to talk about is costs. So here are the costs for this system. So the PEX-A pipe, I bought 6 300-foot rolls, and that was $960, which I think is basically an insignificant amount of cost for this system to be expanded. So I put in a system that was almost twice this the pipe length that is recommended, and I don't regret it at all. I may even put another one in if I had to do it over again. It's for the marginal costs. It's pretty minimal to say put in one more trench. It would have cost me another $600 maybe, and then you get that much more heat transfer area. I had to buy in some more PEX-A pipe, 100-foot roll, of 1 inch inside. Do consider pressure drop if you have to run like all your fluid through some pipes. You want an oversized, definitely oversized if you are putting all your lines through one, or all your flow through one line. Then my mini split, I've actually bought scratch and dent from Ingram's, and that was about $2,000. The taco pump, I bought that used, and it was $171. The Procon pump, that was pretty pricey. I could not find a pump. It actually says 660 gallons per hour. It's actually, but I'm running at half the RPM, so it's half that. And that was pricey, $527. The tank is pretty pricey. And the other major hitters, so there's just tons of little parts, little pipes and fittings and everything I bought, probably $800. The epoxy was expensive for the tank. This, you can't read this, but this is sand, $600, and then the trenching, I spent $2,000 for the excavator, and then I had to fix my neighbor's system quite a bit, so I had to put some money into that. Okay, so final thoughts, just say trenches, just more the better and deeper the better. Do whatever you can to make as many and as deep as you can. The other thing we did not talk about at all is cooling. This system should be ultra efficient in the summer, which would be for any ground source heat pump. But relative to the mini splits, this is going to be way more efficient. So if you're trying to cool your house to 70 degrees and it's 90 degrees out, you're trying to cool it to a temperature that's lower than the outside air temperature. Not surprising, but we'll be using water that might be 60 degrees Fahrenheit, might be even cooler than that. So this system should run very efficient, and I hope to report back to you guys as how it's working. But love to hear your comments and any advice on the technical challenges I have, and take care.